So very good evening. I think we can start now. It's almost 3. So we are in the week 2 of our nanotechnology science and application course. So here we are going to discuss few questions based on the concept which we have learned in the week 2, and along with that we'll solve few questions based on them, and we'll try to see if you have any doubt in the from the videos that is being posted on the NPTEL forum. And also if if you want to interact, if you want to have some discussion, which like in the one way it cannot be possible because of the one way interaction with the recording video is only there. Like, so in the two-way interaction, like you and me, we can interact in that way and try to tackle whatever the doubts you guys are having. Okay, so let me introduce. Okay, yeah. So let's get started, and let me introduce with the platform which we are having, which we have already seen in the last time. That okay, yeah, somewhere over here. Okay, it's visible. So here there is one question by the one of the learner. It was mostly like solving dot solving session. It was not uploaded. So let me tell you that there are the two parallel sessions are running. Like right now, every Saturday I take the class from 3 to 5, and there is one more PhD scholar of our team dealing with the same kind of courses and all, and he is also taking the course, and he's taking from the on Monday 3 to 5. So there will be two parallel session is running on, and the videos will be uploaded like one day after it, mostly one day after it. Okay, so with that, I think that's all, and we can start the discussion. Let me share my screen. Start presentation. Yeah, I hope it's visible. So there is a problem with me that I'm not suitable in writing on the digital pen and paper, so I usually prefer this. So there is some also there is a electricity issue today, and we are facing some light and all those issues, and that's why you can see some zigzag lines are coming. But I think it's visible. I hope so. Okay, so let me check once again the recording part. Yeah. Okay, so we can start. So the topic which we are covered in this particular week, they are as follow. The Feynman talk we have discussed in the last week also, but to a certain extent, like the part two was missing over there, and that's where the we have discussed about the Feynman talk on the nanotechnology, how how the things at the nanoscale or not the nano because he not use the word nano at the small scale work out, like making small nano motors and all those type of stuff we have discussed in the lectures. Then on the next lecture, we have discussed about the thermodynamics consideration on their impact on the nanoscale. To large extent, our this particular week was mostly based on the thermodynamics, phase diagram, and kinetics. We not to a large extent we are not covered we not touch the nano part in it. Okay, in this particular 3 sessions. So in upcoming weeks, we'll do that, and also like we are just collecting the weapons right now, so that in the upcoming weeks, the concept which we learn, we will be easy to digest based on this particular weapons. Okay, so we understand the impact of nanoscale on the thermodynamics consideration, and after that we discuss about the phase diagrams and its stability, like how long, like the particular phase diagram which we see in whatever the like in book which you have seen, like how much time does it take that particular phase to stable so that we can call it to be the equilibrium phase diagram? Does it take 1 hour, 2 hour, or 10 hours, something like that? Okay, so those things has been considered, and we have saw that okay, it take large amount of time for us to call for us to put that particular thing in the equilibrium phase diagram. So whatever we are seeing in the equilibrium phase diagram is after very long period of time holding is been observed. Okay, so that is a phase diagram part we have discussed, and at the last we discussed about the calorimetry, that the exchange of the heat and the isolated system which we are having to build the calorimetry that has been discussed, and heat capacity part, those part has been discussed. So before I get started, let me ask you that if you guys have any doubt in the, the video part, then we can discuss those things. Okay, since there is no, let's get started with the. You can always post your question onto the chat, and also you can, if possible, if you like to, you can also unmute yourself and interact with me if you have any doubt. Okay, so let's get started and let's try to solve this question number one. Let me read it for you. It's a fill in the blanks type. Like, that's the activation energy of the reaction will, that's the amount of product produced. So here is the increase in activation energy of the reaction will increase the amount of product produced. So among these four options, A, B, C, and D, what do you think is a feasible one? The question is telling that the something like here it should be increase or decrease or increase or decrease. Like, yeah, it should be. Venkatesh is saying it's C, and yeah. So see, one more thing is that it can be multiple choice. Okay, so you can there like multiple selection type. There can be two or more than one answers. So we have to look all of them. Okay. So, what is the activation energy first of all? So, for any reaction we are doing, let us say, our initial reactant is over here and the product is somewhere over here. We need to cross some barrier. We cannot directly grow from, sorry, this is the energy. And let us say this is a progress of a reaction. Okay. So, now we cannot directly grow from there, here to here, directly over here, right? We have learned this part in the class. What is there? There is a barrier is there. And this is the activation energy barrier. Like this is a barrier, EA, activation energy. This is something which we need. So what will happen if I increase the barrier? Will the product will form more or will it form less? Right. So if I'm increasing the barrier, let us say, if I'm increasing this particular height, so reactant will need more amount of energy to cross this barrier. Since if the energy is not provided sufficient, so the product will form very less. So in that way, we can see that if we increase the barrier, if the barrier height EA is increasing, then we can say that the concentration of the product, it should decrease, right? Also, let's see what will happen if we decrease the barrier height. So if we decrease the barrier height, EA, if we decrease it, then it should happen the other way around, right? The product will form quite easily. So we can see that the concentration of product, in that case, it should increase. Okay. And that's what it is. So we can see that the option B and option C both are the correct option which we are having over here. Okay. So it's very basic, it's very easy question. So I hope it's clear. Let me know if there is any doubt before we proceed to the next question number two. Okay, that's it. Since there is no doubt, let's move to the next question. It's fill in the blanks type. Let me read it for you. Sorry, not fill in the blanks type. It's true or false type. So we are having indirectly we are having the total of four questions where we have to answer whether its particular thing is true or false. In the assignment, you can see there are the multiple questions you are having a true and false type, right? So this is somewhere over that kind. That kind. Okay. Let's go with the first question. If a reaction is thermodynamically spontaneous, it may occur rapidly. What do you think? If the reaction is spontaneous, according to the thermodynamics, okay, so the energy after the product, if the reactant and the product in this particular reaction will form, there is the energy will increase. So energy will liberate, right? It will release. That is delta G, which is negative, right? And since it is negative, so we can say that it is spontaneous. So if the reaction is spontaneous, does it that it will be rapid? The condition here is that it may be rapid. So it can possible that, yeah, say reaction is thermodynamic, it's spontaneous, we are giving some energy, and it may be possible it can be very rapidly, it can grow, the product will form very easily. It might be possible, right? So the word of may is something very crucial over here. If someone is telling that, okay, if the reaction is thermodynamically spontaneous, it must occur rapidly. Okay, if instead of this it should be must, then our this will be false, right? So now here, a and d A and D are okay. Yeah. So you're telling that A and D are true, is it? So if the reaction is thermodynamically spontaneous, it may occur rapidly. So we can see that this one is true. First one is true, right? Venkatesh. Now let's move to the next second question. If a reaction is thermodynamically spontaneous, it may occur slowly. It is very well possible. See, here is our reactant, here is our product. In the first case, let us say our energy barrier is somewhere like this. In the second case, it might be possible our energy barrier has got increased, right? So in that case, it will be slow, because thermodynamics can only say that it is spontaneous or not. It cannot tell whether what will be its speed. It will depend upon its barrier activation energy, right? So it might be possible, it may be possible that it can be slow. Here it will be fast. In this case, since the barrier is quite less, we can say that it will be fast. In here, we can say that, okay, it can be slow also. The rate at which the product will form, it will be slow. So second one is also, it is also true, right? If the reaction is thermodynamically spontaneous, it might be possible that it will be slow. Yeah, the rate of reaction will be slow. This is also true. Okay. Yeah. So now let's move to the third part. First and second part we have covered. Let's move to the third one and see whether this one is true or false. Activation energy, if we read it, activation energy is a kinetic quantity rather than the thermodynamics quantity. So they are telling that this much of energy, this is the activation energy below, like EA. They are telling this is a kinetic quantity. It doesn't involve the thermodynamics in it. So what do you think in that? Whether it's true or false? Whether EA is a thermodynamic quantity, or whether it's a kinetic quantity? What does it perceive? You can write T for the thermodynamics and K for the kinetics in the chat box if you like. So on an average, we know that this top part, this activation energy, yeah, it's kinetic perfectly when it is. So we can see that this barrier is something which is leading, deciding our rate, like at what rate particular thing is happening, and that's why it is kinetic factor. And so we can say that activation is a kinetic quantity rather than the thermodynamics quantity. It is true. And with that, all starting three, we found that they are true. Let's move to the next question. Question number, like last part. If a reaction is thermodynamically spontaneous, okay, reaction is spontaneous, it must have a low activation energy. See, it might be possible it can have a low activation energy. It doesn't guarantee. If thermodynamic is spontaneous, its low activation energy doesn't guarantee, right? And here the word has been used is must, right? And so it doesn't guarantee anything. Thermodynamic cannot comment upon the activation energy whether it's high or low. And so in that way we can see that our last one is false, right? Please let me know if there is any confusion, any doubt in this. No? Okay, that's great. So let's move to the next question. Question number 3. Okay, so let's say this. The question is telling that, let's read the question first. In a binary system of A and B, so we are having the binary system of A and B. Yeah. A liquid of 20% A is coexisting with a solid of 70% A. Okay. So there is a liquid is there and there is a solid is there. So okay, let's make one structure over here. This is some solid and it is surrounded by the liquid. Okay. Let me just mark them as a crystal type. Okay. A liquid has a 20% of A. So this liquid is having 20% of it. And the is coexisting with a solid of 70% of it. So the solid is having the 70%. What does it mean? Since this is 20% of A, it means that the remaining one is the 80% of B. Right? It's obvious. And 70% of A, it means that it will be 30% of B. So if I draw this, let's draw the phase diagram. Here they have said that only solid and liquid are existing together. Okay. So let's consider that part. Let's say this is liquid, this is solid, and in between we are having the liquid plus solid. I made a diagram like this. I not made it like this one. There is a reason, because the liquid is the one having the low percent of A. Sorry, they are having the more of A, and that this one solid one is having the more of. Sorry, solid is having more A. Okay, I should not make like this. This is a wrong diagram then. The right one will be this. This is liquid, this is solid, and the solid is having, if this is A and this is B, and we are moving in this particular direction, the percentage of B is increasing. Okay, so now what is here, that the A is having, the solid is having 70% of A, that is, it is having the 30% of B. If I'm marking from the direction of the B, then the solid is having 70% of B, sorry, 30% of B. So this point is, and liquid is having somewhere over here, this liquid, the one which is existing with the solid, this is having something like, we know that this is 20, and then it will be 80% of B. Right. Now let's move ahead. If the overall composition having the 70% of it, this entire thing, if we combine them, they are having the 40% of it. That is, they are having the 60% of B. I could have done the entire thing in the terms of A, but anyway, okay. Let us, we are somewhere over here. So our actual composition is lying somewhere over here, and this is corresponding to the 60% of B. Somewhere this is 60% of B. Whether it's better I should make one new diagram. It's quite congested right now. We are over here. This is our diagram. This is A, B. Our composition is lying somewhere over here, because we know, see, this is liquid, this is solid, and this is liquid plus solid. We are not lying over here in this particular region solid. We are not lying in the liquid, because we know that in our case, both of them, liquid and solid, are existing. So we are lying somewhere over here. And the overall composition is something around the 40% of A, that is 60% of B. So if I mark from the perspective of B, so this is 60% of B. And its solid part, its corresponding solid part is somewhere over here. Liquid part is somewhere over here. And so we mark that this is 30%, this is 80%. So this is 30 and this is 80. What we need to find, what is the fraction of solid and liquid present in it? We need to find their fraction. Okay. So what is a fraction of the solid is present and what is the fraction of the liquid is present? And we know that from the phase diagram, it's very easy that just by line that, just by drawing the tie line and applying the lever rule, we can do that. Okay. So let us, we are starting over here. So we know that if we apply the lever rule over here, this is considering this to be the tie line. Okay. So what we'll do, let us say we are try to find the fraction of the solid. So what we'll do, we'll take this particular length which is away from the solid part. See, we are dividing this entire section in three part. Sorry, in two part. Okay. One is this and second part is this. So solid, liquid, and this is our actual composition. So we are dividing them in this particular line. If we want to find the fraction of the solid, first we have to take this length. What is this particular length? It will be nothing but 80 minus 60. This is 80 minus 60. And divide this entire thing by the entire length. And the entire length will be 80 minus 30. Okay, let's try to solve that. Solve it. It's very easy. So 80 minus 30 is nothing but 80 minus 60 is 20 and 80 minus 30 is 50. So we can cut them down. So we got that percentage of fraction of the solid which is present over here is 0.4. So what is the liquid fraction? We got the solid fraction. In the similar manner, let us say someone want to find the liquid fraction. So what they can do, they will go away from the liquid. They will take this particular length on the numerator and divide this by the entire length. If you ask that why this is like that, why we are not, if we are dealing with the solid, we should divide, numerator should be on the solid. This is how the lever rule has derived the derivation you can see. And you will find that, okay, yeah, this is how it is. If you want to find the solid fraction, you have to take this particular length and divide it by entire length. This is how it is. And so since we find the solid fraction, and we know that only the solid and liquid is the one which is existing. Solid we know. The remaining is a liquid only. So the remaining, the liquid percentage will be nothing but 1 minus 0.4. 1 minus solid. It will be 0.6. And that's how we got that. Okay, if this particular information is there, like if only we are knowing that what is the overall composition and what is the composition of the solid and liquid, we can find their fraction of the phases. What is the fraction of the solid and what is the fraction of the liquid? It's not only limited to the solid and liquid. We can apply this to the any number of phases which we are having. Let us say alpha and beta, two solids are having, or there is a, in the three phase diagram, there is also a thing like the, instead of making the tie line, we are making the tie plane and we are cutting them down. So those things are later part. This is the very easiest part till now, which we have learned. Okay. So don't think that it is only applied to the solid and liquid. It can apply to the any number of phases, any different type of phases, whether it's two liquid, two solid, one solid, one liquid. Okay. So with that, we have finished this question number 3. Please let me know if there is any doubt. Yeah. So with that, our answer is first one. No? Okay. That's great. So let's move to the next question. Question number 4. See, by mistake, I made this question quite lengthy, question number 4. That's why I'm trying to hide it. So we'll read it in a fraction way. Okay. Let's read the question. Which option correctly complete the following statement? Okay. So we need to find the option which is completing this particular statement. A catalyst can act in a chemical reaction too. Okay, so what is the role of the catalyst? Indirectly, they are asking. Okay. Question number, the first option is that it will increase the equilibrium constant. Yeah, perfectly right. It will decrease the activation energy. It is one of the role of the catalyst, right? Perfectly right, Venkatesh. What about this first option? Will it increase the equilibrium constant? Does it affect the equilibrium constant? Right. The question is that will the catalyst affect the equilibrium constant? What do you guys think? What is the equilibrium constant usually? What is equilibrium constant? It is a mostly we can roughly we can say that it is a ratio of the product to the reactant. Right. Catalyst can only enhance the kinetics, right? Since it is decreasing the activation energy, just like Venkatesh has said, and previous in the first question we have seen that if the activation energy has decreased, the product quantity will increase. See, so the product quantity is increasing, but also that it's only the rate has been something which is increased. Okay, if we wouldn't have the use the catalyst, we would have got to the same product, but after a very long period of time. Right? So it's not affecting the equilibrium constant. It's not affecting the concentration of the product and reactant. Okay, so we can say that okay, it doesn't affect the equilibrium constant at all. So we can say this is not our desired. What should I write? Correct option? No, let's cut it out. Second one, lower the activation energy, just like Venkatesh has said. Yeah, catalyst has this particular role that it will lower the activation energy. So if the activation energy is somewhere over here, if I'm using the catalyst, I can decrease its activation energy further and I can go somewhere over here. Again, it can decrease. Lower the activation energy, perfectly right. Second, third part is telling that provide the new path for the reaction to occur. What do you think? Is it true? Uh, will is the catalyst. How the catalysts are playing role in this particular reaction. So let us say A and B. Okay, better I write over here itself. A and B should react and form something, let us say C. D is, let us say, our catalyst. So it was very difficult. Let us say A and B was very difficult for them to react. So what D has did, D went to the A, it reacted and it formed something, let us say E, or better instead of calling E, let us say A and D. And then again, this A and D, let us say this A and D which is formed, it has more reactivity. Think I do, yeah, perfectly right. So yeah, so we can see that over here that AD will react with B and it can form C. So instead of going by this path, what catalyst has done, it has created the new set of reaction, new path similar to the lowering the activation energy. Yeah, perfect. Somewhere over here. Yeah, it's lower the activation energy by this particular method only. By either it can supply some surfaces to the surface for our reaction to occur. It can facilitate it in that way, or it can make some bonding and all and participate in the reactions in this way. So we can see that this C option is a correct one. Perfectly right. Let's What about the D? Get consumed in the chemical reaction. Does it get consumed? False. It doesn't get consumed. See here, D was our something, and we got final C, and here we will get our D back. So it is started A reacted with D in the initial state, and at the finally we got our D back. That we got our catalyst back. So it doesn't get consumed. It is just like okay, I'm going into the reaction. I will facilitate them, and I will be coming back. You're not getting consumed over here, right? So this one is a false one. We can say this is false. Now E, change the equilibrium concentration of the product, not change even after the end of the reaction. Yeah, perfectly right. Not change even after the end of the reaction. It's remain as it is. So, we are done with B. What about E? Does it change the equilibrium concentration of the product? if it changes the equilibrium concentration, then it should affect the equilibrium constant. So we know that equilibrium constant is not altered by the this particular by the catalyst. Okay, so if we are achieving the equilibrium, let us say, whether we are achieving the equilibrium by the use of the catalyst or we are achieving the equilibrium without the use of the catalyst, equilibrium has achieved, right? Once the equilibrium has achieved, the product phase, the product which is formed, they will be having the same concentration. Equilibrium has achieved. All the catalyst will do, it will lower the activation energy, and it is not gonna change their concentration. It is only going to increase the kinetics. Okay, so once the equilibrium has been achieved, the concentration of the product will remain as it is. So it's not gonna change the catalyst is not gonna change the concentration of the product. Okay, so this statement is false, right? Great. Let's move to the next one. Does not affect the reaction energy path. So now this is something. Does it affect the energy path? So what is our energy path? Over here we can see initially without the catalyst, the blue one without the catalyst, and this is with catalyst. Oh, both of them I'm writing W only. Okay, let's. This is with catalyst and this is without catalyst. In the first case, this is the energy. So the energy path was like this. In the second case, it is decreasing the energy path. The energy path has been changed, right? It will affect the either increase or it will affect the path by lowering. Yeah, perfectly right, Venkatesh. So it does, yeah. So change the equivalent. No, we are done with this one. Okay, does not affect the reaction energy path. It's false, right? It does affect perfectly, perfect. So again, this is not something which we want. Like we are looking for the correct answer. Always decrease the rate of the reaction. Is it? Does it decrease the rate of reaction? It might be possible, but does it always decreasing? No, it's not that the catalyst is gonna decrease the rate of the reaction. Majorly, we use it to increase the kinetics, increase the rate of reaction. But even if it is decreasing, it's not that in certain case, let us say, possible that it might decrease, but it's not always the case over here. They are saying it's always. No, it's not. So again, this is false, right? So G is also gone. Let's move to the next question. It will always increase the activation energy of the reaction. Again, this is something always word is there, and always remember that this must and must always, those kind of words, it will always be leading to something false statement. Again, this is incorrect. Participate in the reaction. Now, get consumed in the reaction and participate in the reaction. There is a difference between them, right? Does it participate in the reaction? Yeah, it is participating in the reaction. It participated in the reaction, but on an average, it is not getting consumed. Does it participate in the reaction? Yeah, it's true that catalyst has changed the path of the reaction, and it is not getting consumed, but it is participated in the reaction. Yeah, perfectly right. It's true. And so with that, we have finished this question number 4. It was quite lengthy, if you see, and that's why we did it on one by one. Okay. So with that, question number 4 is over. If there is any doubt in this particular question, please let me know. Okay. Since there is no, let's move to the next question, question number 5. I hope it's visible, but still let me read it. That Let's focus on the question first, then we'll go with the options. Consider 1,000 particles. We are having the 1,000 particle having the aggregate of the 1,000 joule of 10,000 joules of energy. Okay. Which of the following statement state true regarding the energy distribution? Okay. So among this, which one is a true regarding the energy distribution? Okay. So we are having in total, we are having the 1,000 particles, and their energies, the overall, the aggregate energy which we are having, it is a 10 joule, 10 kilojoule, 10,000 joule. So on an average, if we say, again it's an aggregate, it's again a rough estimation. Now let's go to the next this fourth point which we are having, that in the reality, how the energy has distributed among these particular particles. We have seen in the lecture, right? We have seen that how the energy among the particle will distribute. So let's see that energy particles, each particle will have the 10 joule of energy. Is it? Can we say that we are having the 1,000 particles, and in the reality each of the particle will have more energy? See, even in the gas, if we talk about, let us say, they are keep on colliding with each other. On an average, we can say that okay, this particular gas having this particular kinetic energy entirely, having the, let us say, uh, 1 kilojoule of energy this particular gas is having. But among that, there will be a particle which will be having even higher energy. There might be possible that will be having lower energy compared to the average value, right? It's like our class. Let us say a class is there of 100 students, and someone is scam. Some principal from the other school has scam and asked teacher that what is how the class is performing. So let us say teacher is telling that okay, they are getting the very good number, and the overall is 80%. 80% mark they have got in the out of 100. So they are the our teacher or professor is telling the average number. There might be possible that the few student will be having the more, and few student will be having less, and it even possible that some of them are having the that 80 number itself. So each particle will be having the 100 joule of energy. It's incorrect. Let's go with the B1. All particle will be having the energy greater than the 10 joule. If all particles are having energy greater than the 10 joules, then the entire energy will be more than the this particular energy. Again, this is incorrect. Equal to is also eliminated because we have eliminated the first part. All particle will be having energy which is less than the 10 joule. This is again not the case. If all of them are having the energy less than or equal to the 10 joules, then the entire energy, aggregate energy, will be less. We can eliminate this. There will be the energy distribution in a way that some particle have the energy greater than the 10, less than the 10, and equal to the 10. Yeah. So it might be possible. Let's say these are the energy state, 10, 20, and let's say this is 5. It might be possible that most of the particles, let us say out of 1,000, let us say 500 will be over here. It might be possible that instead of 20, let's say 15. So it is also possible that it will go the 5, this 5 energy, 5 joule of energy, particle having the 5 joule energy will be comparatively less, but they will exist. Okay. So let us say this is having the 500 particles, and this is having the 250 particles, and this one is again having the 250 particles. So there will always be the distribution of energy. I just state about the three states of energy, but in reality there can be a multiple state. Yeah, so option D is the correct option. Yes, Ram, it is. And so that's how. What about the first case? If we talk about, there will be what they are saying. Okay, we are having the, let's say we are having the three states. Okay, they are saying the all the particle will be having the 10 joules. That's it. Remaining two cases was not even feasible because the energy conservation was not there, and that's how we have completed this question number 5. If there is any doubt in this particular question, please let me know. Okay, since there is no, let's move to the next question. Question number 6. Let's read it first. Consider the following reaction where x is transforming to the y and vice versa y can transform to the x also, like the equilibrium. Okay. The conversion of x to y release 10 kilojoule per mole. Okay, they are releasing. Okay, it means that when the x is converting to the y, the since it is releasing the energy, it means that the y is comparatively more stable, right? So y is having the lower energy. So this is y, and this is x, and let us say this is our energy profile. Let's read. So they are telling that it is releasing the 1000 kilojoule of energy. So it means that the difference between these lines, it's a 10 kilojoule per mole. This is the amount of the difference is there. This much amount of the energy will release. Now let's move ahead. And has an the conversion of x to y release this much of energy and has an activation energy of 4 kilojoule per mole. So to convert x to the y will need the activation energy, and that is something around 4 kilojoule per mole. Okay, okay. Since it is having the activation energy, let's make it, and the activation energy of 4 kilojoule per mole. So this particular height is around 4 kilojoule per mole. Let's not bother about the unit because units of both of them are same, right? What is the activation energy of the reverse reaction? Now they are asking that, okay, x has converted to the y. It required 4 kilojoule of kilojoule per mole of energy for the activation, and also it is liberating the energy of the 10 kilojoule per mole. Now they are asking that what will be the activation energy for y to convert to the x. It's EA we want to find. So what do you guys think on this? Like, okay, 10 kilojoule. Yeah, Venkatesh is telling it's 10 kilojoule. Okay, so let's see from the perspective of y. Y is over here. Y need to climb in order to get to the x. It has to climb a barrier. Let's say till what it is climbing. It is going by this path over here, over here, over here, and over here, and over here. After this, it is decreasing. So it has to climb this much of energy. And what is this much of energy? Okay. So the energy which is liberated and the activation energy of this one, their addition will be something which we will get. So 10 plus 4 will be nothing but 40. So this much is amount of activation energy that Y will take to convert to the X. Right. So that's how it is. So we can see that the best option will be, yeah, option A. Please let me know if there is any doubt in this. I hope it's more related with the thermodynamics and kinetics part, activation energy part. Okay. Okay, yeah, that's it. Okay, since there is no doubt, let's move to the next question, question number 7. Yeah, so now we have to do some math, the following very childish type, right? But still, let's do it. So let us say these are A, B, C, D, and let's say these are 1, 2, 3, and 4. We are having the thermodynamics, kinetics, catalyst, and calorimetry. Here are the terms, that is activation energy, measure change in the heat, feasibility of the process, and alter the activation energy. Among these four options, what do you think which is the best fit for the thermodynamics. A will match with what? Does it talk about the activation energy? Does it talk about the measurement of the heat or feasibility of the process? Or it talk about the altering the activation energy? Right? Yeah, it's talk about the feasibility. So we can say the third one. Thermodynamics will be matched with the feasibility. A will match with 3. What about B, the kinetics? Kinetics among these three, remaining three, feasibilities has already gone. Does it talk about the activation energy, measurement in the heat, or does it talk about the altering in the activation energy? Activation energy it is, yeah. So kinetics we can say it will talk about the activation energy. So B will is going to match with the one. And catalyst, measurement of heat, does it talk about? No way, like there is no way that it's talk about the measurement of the heat. Yeah, alter the activation energy EA. So perfectly right. So catalyst C will going to match with the 4. And calorimetry has left. And we also know that calorimetry is something which is usually used to measure the change in the heat. Okay, so with that D will match with the, and that is all for answer. Okay, so I hope it's very clear. But still, if there is any doubt, please let me know over here. Since there is no, let's move to the next question. Question number 8. Okay, let's read this question. Sorry, let's read this question. Here, what they are saying that the equilibrium phase diagram mentioned in the phase diagram, sorry, equilibrium phases mentioned in the phase diagram are obtained by holding the sample at a particular state for 1 hour, 10 hour, 20 hour or long time. Particular state, what does it mean? See, first of all, they are asking about the phase diagram. Okay, so we can say that any phases that is having we are having in the phase diagram. Okay, so in phase diagram, if we are mentioning anything, let us say this alpha phase is present, or let us say this liquid is present. For a timing, let us say we are having the alpha plus beta with us over here, and we started heating it up, and we started heating it till it went to the liquid phase. Now this entire solid which we were having with us, now once we heated it up, it has converted to the entire liquid. Now they are asking that okay, you heated it up, but for how many time you have hold it? 1 hour, 10 hour, 20 hour, or long time, so that after which you have mentioned in the phase diagram. Okay, we know that any transformations will require a lot of time, right? And so whatever is mentioned in the phase diagram, it's like it's holding for an infinite amount of time. Infinite is very exaggerated, but let us say 1 year, 2 year, 3 years, something like that. We can hold for those much amount of long period of time and obtain the phase diagram. So I'm hitting it up and holding it for a very large amount of time, and that's what mentioning over here. If alpha plus beta is mentioned over here, it is again, let us say I was having this liquid bag, and now I want to like I heated it up and convert it to the liquid, hold it for a very large amount of time, and find that okay, this particular phase is there in this particular liquid, like this much amount of alpha and this, sorry, this much amount of A and B is there, and how their structure are. Now I've studied that. Now I want to go back to my alpha and beta. Now I'm cooling it down. I'm cooling it down. Let's say this is a room temperature, 25 degrees Celsius. Now let's say our sample has reached to the 25 degrees Celsius, but still we are holding it. Like, this entire cooling process will take a lot of time, and we are holding it for very, again, we are holding for a very long amount of time, so that at the end we know that what is the final phase which is present. It's a, for timing it might be possible that this liquid plus beta phase is there, and this liquid is taking a lot of time to convert to the alpha. It's to break into alpha and beta. Okay, so that's why we hold for a very large amount of time, and then only we mention in the phase diagram. Okay, so among this, no, no, 20 hours, no, only the long time holding might be even several years. It can take a lot of time, right? And that's how the question it was. So please, so from now onwards, if you read any of the phase diagram, you will say that okay, yeah, it's something which is very, it take a lot of time to obtain this entire phase diagram structures and all. And so usually the thing which we are doing in the, let's say, steel making and all, like Tata Steel and all those steel plants, we are dealing with the kinetics also over there. So that and also we don't need this particular, let us say, perlite structure. If let us say it's very soft, it can deform easily. So there is a lot of alteration with the kinetics and all. So we shouldn't think that we will always need the equilibrium phases only for us to deal in the real life. So for example, if my cell phone is made up of the certain material, it's not that it has to be made up of the equilibrium. It might be possible that equilibrium, the phases are the one which are the weaker and like not having the desired property, desired properties. Okay, I use the word might. Okay, so that's how it is. So this phase diagram take a lot of time to obtain. Okay, let me know if there is any doubt in this question. Okay, if there is no, let's move to the next question, question number 9. So this will be our last question of this particular session, and let's try to solve it. It's numerical type. So here, let's read it first. A copper block of mass 3 kg is heated to a temperature of 450 degrees Celsius. Okay, forget to write degree. So we are having the copper block, and it is having the mass of 3 kg. And we have heated it and put, like we put it in the furnace and we heated it, and now the current temperature is 450 degrees Celsius. Okay, this is the temperature of the copper block. Now we took it out and we put it in the large ice block. So we are having the very large chamber which is made up of the ice, and we are putting our copper block inside of it. Let's say somewhere something like this. Now we have to find the maximum amount of ice that can be melted with this. Okay, two things are there: specific heat of the copper we has been given and the heat of fusion of water. These things are mentioned. We need to find, okay, this much the copper we were having, we put it in the furnace, the temperature was 450 degrees Celsius, we took it and put it in the a large ice block. Now now we want to know that how much quantity of this ice can be melted. Let's assume that this ice is very large in amount. Okay, very large in amount, and it can melt, keep on melting as long as you keep on providing the temperature. Again, there is one word has been mentioned over here, maximum. We'll see that why this maximum word has been used. Okay, so now let's see from the perspective of the copper. So copper, how much amount of heat it is having. Okay, so we know that delta H we can find by integral of mcp dt. Mass has been mentioned over here. This is for the copper. Let's say delta H for the copper. Mass we know that it is of the 3 kg. Cp has been mentioned over here and it is just a single number, right? Cp can also be in a variable form in the form of the temperature. But right now, the one which is mentioned in this question is constant. So we can take it out. So M we took out, Cp also we took out. And what is remaining inside is integral of dt. That is final minus initial. T final minus T initial. Okay, so let's say this. The overall mass, which is, let's again write that delta H is equals to the M Cp delta T. Mass we know over here. Mass is around 3 kg. We can write it over here 3 kg. Let's also put the unit side by side. Cp we know. Cp is 0.39 joule per gram Kelvin. And then we have to write the delta T. That is final minus initial. What is final? The final, if we are putting in the ice, okay, if we are putting something in the ice, its final temperature will be, once the entire thing has melted, all the heat has been transferred, the final temperature will be nothing but the ice temperature. That is, we can assume it to be the 0 degree Celsius. Minus initial was 450 degrees Celsius, right? See, again, there is a problem with the unit over here, Kelvin and degree Celsius. But remember, if I convert this to the Kelvin, the factor of 273 will add over here. And so over here also, if I convert this to the Kelvin, on an average 273 will be cut out and this will give me the unit of Kelvin itself. So we can directly cut this units and we can write that 3 multiplied by 0.39 multiplied by 450, and since minus term is here, it means that 157 kg of water. Perfectly right, yeah. So uh, Venkatesh is telling it's 1.57 kg of water is something which you will get, right? That's the right answer. Let's see how we have arrived to that, how Venkatesh has solved it. Okay, so here negative sign is there. A negative sign is something is telling that this will be the used to, this is the energy which is liberated. Okay, and the unit we can say that kg joule per gram. We'll see that what this will be multiplication and all, see it later. Delta H of copper. See, now this much amount of heat has been liberated and it has been supplied to the water. Sorry, ice. Now what ice can do? Ice will melt. In the process, these things are happening. A time will arrive where we were having. We are having the ice also. We are having the water also in the liquid state. Right. Copper is in contact with both of them. It is providing the heat to both of them. So it might be possible that the temperature of water will also increase, right? Instead of zero, it can also that it will increase. It's not like the entire heat is converted to the, it's taken by the ice only. And that's why this maximum term has been used. What's the maximum amount of water that we can get? And so we are here assuming that the water is not consuming any of the heat to increase its temperature even further. And even if it did it later on, it will be like until unless it's not evaporated out, it will be again given back to the ice. So now what we are having, this much amount of energy we got, that okay, this much amount of energy has been released, and now we need to find that the amount of the water has been, this amount of heat has been given to the water. Its heat of fusion is there. Okay, so the temperature is zero only, and after fusion it will be, we can say that it's zero only. So the m into delta h of fusion, enthalpy of fusion. So mass times multiplied by hf of, this is of the water we are talking about. Okay, till here we talk about the copper. Now we are talking about the water. Ice. We are talking about the ice, and we know that the fusion of water, the heat of fusion of water is 335 joule per gram. So it is 335 joule per gram, and we can equate this to this particular quantity, right? See, if I equate this to joule per gram will be cancelled out, and I can get the mass m will be 3 multiplied by 0.39 multiplied by 450, and the whole divided by the 335, right? So let's calculate it. Where is my calculator? Yeah, let's see. So on the numerator we are having the 3 multiplied by 0.39 multiplied by 450, and then we have to divide it by 335. So that's just like the Venkatesh has told us that it's like 1.507 kg. Yeah, perfect. And so yeah, so it was 5 to 6.5. Okay, okay, yeah, that's great. So this is has been 5 to 6.5, and with that we got that okay, this our answer is option B, and with that we have completed the question number 9, right? So please let me know, is there any doubt in this particular question, question number 9, or any question that we have discussed till now, so that we can have a even more detailed discussion on those things. Okay, since there is no doubt, we can conclude our today's session, and please try to submit your assignments by this particular week. I think we are having some deadline to us. Okay, yeah, that was it. Was also a great interaction from your side. Like it's quite relaxed manner. Okay, so with that we can finish this particular talk. This is the question number 8. 7 we did the math the following. Question number 6 we did some energy uh, calculation was there, and so on and so forth. See, if you say this entire thing that we have discussed it today, most of them was not related with the nanotechnology, right? But we are studying that because in the further week, which when we are going to discuss the nanotechnology part, the nanomaterials part in that, the physics part of those, this particular type of interaction, like this particular knowledge one should have. Okay, especially the thermodynamics part is going to be elaborate even more in the upcoming weeks. Okay, so with that, I'm taking my leave. And if there is any doubt, you can always post on the doubt forum, Q&A forum, and obviously I will respond to that. Okay, that was great. Thank you all. Bye bye.